So we're bringing in Duan Lightfoot. Duan's going to share with us what's actually happening when you deploy LLM inference on Kubernetes. So I'm super excited for this. We've just lost Duan.
Oh, we lost Duan completely. Okay, well,
we'll just wait and see. I
think you scared him with that topic.
Probably.
He was probably like, "No, I came to talk about something else." I think he's going to show a demo too. So that's always a, we make sure we say a lot of prayers to the demo goddesses. Don't pray to the demo gods; they're not in charge. You got to pray to the goddess. So we have done our little demo goddess dance, and so hopefully that works out well.
Well, while we're waiting, we can do a shout out to our sponsors. Again, for those of you who weren't here this morning, in order to make this happen, it is a community-run event. We all give our time and energy to curating the best speakers, but we do have sponsors so that we can get this platform and make it happen for you. So Akamai is a sponsor, Intuit, of course, and Intuit is kindly letting us use their office today, as well as Buoyant, Relax AI by Sivo, and Teleport. So thank you all to that.
Thank you so much. And of course, our community partners, Merge Forward, in this case, and of course all the KCDs that supported us, San Francisco Bay, Texas, the other cities around the world. This really is a community event. There's lots of CNCF ambassadors that have been working behind the scenes and have been presenting today, including the two of us. Danielle and I are CNCF ambassadors, have been for quite a while. I feel like I've been a CNCF for like 5 years at least, or 6. We started running early days meetups here in the Bay Area on Kubernetes back almost to the beginning of Kubernetes. So we've been ambassadors for a hot minute, and I see we have Duan back. Yay! Is everything good over there?
Yes, everything is good. I needed to fix my screen share on my new laptop, so.
Oh, courageous, doing this from a new laptop even. We did test out all this stuff, and then Duan decided to throw a wrench into the system and change everything. Okay, but we believe in you. We know that you're probably the most technical person on our agenda today. So are you ready? Everything's working?
Yes, everything's working.
Okay, then we're going to take ourselves backstage, and we'll let you take it from here. Thanks.
Awesome. Thank you. Hello, everyone. My name is Duan Lightfoot. I am a developer advocate at Akamai focused on AI engineering. Today, we're going to be talking under the hood, GPU inference serving on Kubernetes. Now, when we talk about GPU inference and what that actually looks like, with traditional AI and how we've been using it, oftentimes we will use a provider like OpenAI or Anthropic, right? And they pretty much handle the inference for us. So you take a prompt, you send it to them, and then they generate a response. Now, we're used to that response coming back in a streaming way, meaning token by token, and it goes pretty fast. And it's improved. If there's any latency in that, that could be the difference from growing your customer base to losing a customer base because another provider provides a better experience. So for those of you that are used to that experience, that's great. But in today's market, as technology is progressing, GPUs are progressing, and our understanding of AI and our use cases are changing, oftentimes you may want to be in an air-gapped environment, or you want to be self-hosted, or you have a unique need where you want to take a model and fine-tune it and host it yourself, right? Well, you can do this on your laptop, and it works fairly well, right? You could take a GPU, whether it's on your Mac that has unified RAM, right? So rather than having like an NVIDIA video card, it takes and combines basically the CPU and the GPU and creates something called unified RAM. So that one card supports video and it supports CPU processing. Or you can buy a NVIDIA GPU off the shelf, have a desktop, and perform inference that way. And it may work well. You may get 30 tokens per second or something. Now, imagine taking that application that you built and serving it out to your team. Now you have 3 to 4 users. and they're all invoking this, your desktop, your laptop, or whatever. And now the performance is kind of slowing down. Let's say you were getting 30 tokens per second. Now they're getting 10 tokens per second, but it's still working. Okay, the performance, it may not even be really noticeable. So now you open it up to more teams, and now they're performing inference. And now all of a sudden, they send a prompt and they're just waiting and waiting and waiting. And before they get that first token, it takes about 30 seconds to a minute. Now, with traditional applications, you would get some type of timeout. You would get some sort of status code, but with inference, this is totally different. Totally different. And this is what we're going to talk about today. Now, I kind of broke this down, but we talked about time to first token. This is something that you really need to think about when it comes to inference. There are three things that we kind of measure that we care about most, but the first thing we care about when we're providing a good experience to our users is how long does it take for them to get that first token. I mentioned before that when it comes to inference, you don't have the traditional status code of 200, 300, 400, 500. You kind of just wait because it's not a CPU thing that's the problem. It's more of a GPU, and the CPU itself may function great. The computer's working, but when it comes to that workload that's being handled by the GPU, that's what's actually slowing down. And so when we think about this, there are some things we kind of need to unlearn from traditional applications, right? So from a web service standpoint, you have the CPU or the network. And I like to think of this as I have a network engineering background. So when you have Ethernet, let's say you have 100 megabit Ethernet. Well, you can get 100 megabits per second, right? Well, it's not necessarily changing the speed. It's how much information can actually fit down that pipe, right? It's not going faster. You just get more packets at the same time that comes down that pipe. Change it to a gigabit, same thing. More packets go down that pipe. When it comes to inference, now the bottleneck is memory. How much can it process down a particular pipe, right? So that's what's going to determine like not necessarily your time to first token, but every token after that. How long is that actually taking to generate, right? That interleave processing after that first token. How long is it taking the matrices and the calculations and the predictions to happen within the GPU? And then the per request cost. With traditional web application, that's going to be, static. You pay for your bandwidth, you use that, and it's good. But when it comes to inference, something weird happens, right? Because as your users use the application, you have something called the context window. And if you remember 3 years ago, context windows were about 8,190 tokens, 92 tokens or something that you could fit in that context window, which was roughly about, let's say, 16,000 or 30,000 words or something that could go into that context window. Maybe not even that much. Yeah, something we'll say about 30,000 something words that go in the context window. Now you have context window out of 1 million contexts. As you'll see here, that's a pretty beefy GPUs. So if you look at the price of GPUs and the amount that it actually costs, I'll show you today why that context window makes it different to predict your user base and how much they're going to consume, because you may send a simple question like, what is the capital of France? Or you may send like a 1,000 word or 10,000 word prompt, and you want to generate a response. That takes calculations, and that's going to increase what you call the KV cache, which we'll talk in a minute. And then we talk about concurrency model. So that's going to be stateless. As people send requests, it can handle that. Well, when it comes to the concurrency of the inference, now we're talking about that KV cache state, right? Because that isn't going to be static. It's actually going to grow. How do you control that? And it needs to actually sit there for the whole time that the entire request is generated. That state needs to maintain there until it's finished. And then the failure modes, again, I mentioned this before, you get 500 errors traditionally, but with inference, the latency actually changes, because as the system degrades, you're not actually getting errors. It's just degrading silently, right? And then scaling. This is where we get to the Kubernetes part, because with traditional scaling of an application, you can add more pods, right? You have a cluster, you have nodes, and you add more pods as you gain more users. Well, with Kubernetes in K8s, it's not as simple as adding more pods. You actually need to add GPUs, and you'll see why, because each pod will have its own GPU. Now, you can configure that, but adding more pods, they all got to use pretty much the same GPU, right? And so that's not actually increasing the capabilities or the bandwidth for your users. That's just adding more burden on that GPU. So you actually need another GPU and kind of scale out that way or scale up. And we'll talk about that as well. So when we look at the target architecture for what we're going to discuss today, we're building vLLM on LKE. That's going to be the Linode Kubernetes Engine. And so vLLM is a way for us to be able to host inference either on your laptop or on a container or desktop and serve a model to your customers. It gives you a ton of flexibility that you can see. But when it comes to the cluster standpoint, we have a firewall or cloud firewall that protects our node balancer. And then behind that node balancer, we have our cluster. And then from a pod standpoint, we have our GPU. In this example, we have an RTX 4000, which has about 20 gigabits of VRAM. We start with this because it's simple, easy to get started, doesn't cost too much. And I'll give you some information at the end so you can get started and get 300 credits as $300 in credits for Akamai Cloud as well. And then from there, you have the GPU, and then we have vLLM, which is going to be used to serve the model. But we can't actually leave the model sitting on the pod, because if you know anything about containers, they're kind of stateless. So if we need to destroy that container, or we need to do anything with that container, we actually don't want to download the model again, because what will happen is this. If you download the model every time you need to spin up a new pod or restart the pod or do any updates on the pod, then you're going to have a real issue with the experience of a user. They're going to have to wait like 10 minutes because the cold starts, right? So you actually want to put that on a block storage and then use it as you need it. And so another thing we need to think about is, I mentioned that you have one GPU to one pod. Another thing that's different about when you're building out these containers and these pods is from your laptop or from a traditional server, is that the drivers for the pod or the container don't actually live on the pod. They're not in that container, right? You actually install those on the node. So the way this actually looks is you have your container pod, and what it does is it requests the NVIDIA GPU of one pod, one GPU, and it mounts it to that container, right? So it mounts it so it knows it's there, but it really doesn't know it's there yet. And then you have a scheduler that says, okay, I need to know, the node needs to know that there's actually a GPU resource to get there. So the scheduler needs to know this. And so to do that, you need a device plugin daemon set that advertises the hardware to the scheduler. And then that driver daemon set is installed with the host kernel. So that way the drivers are loaded into the host. They're not in the container, they're in the host. So the host will know about the drivers and get a container everything it needs. So it's mounted when you spin up and use that container. So everything is kind of done on the actual host, so it knows about the GPU. All right, so we're actually going to look at a demo here right now. So we're going to look at bringing up a cluster and a vLLM pod that's healthy. All right, so I have my Mac. I'm going to bring up a new window. So we'll bring up a new window so we can look at our environment as well. So in this environment, I have everything that we need to be able to perform inference. The container is already spun up just so we can save on time. So the first thing that I want to do is be able to connect to our, and you'll see this, what we're running, our Grafana. So we're going to go into Grafana here in a moment. I put 300, we need 3,000. So now we're going to open Grafana and we'll log in. We'll log in with our account. And then we'll make sure that we can get in here with everything we need. And if you all have questions, please leave them in the chat. All right, so we'll go into Grafana, and I have two different dashboards here. So the first dashboard is actually so we can see the GPUs and see, okay, we can see the GPU temperature, we can see the memory temperature, we can see everything about the utilization, the power usage, the buffer memory use, and you can see this is static. I'll explain why this is static here in a moment, but this is throughout this demo, this GPU is going to maintain at 18 gigabits, right? That's how much VRAM we're actually using. This is not going to increase, and I'll show you that here why in a moment. And so we come into our Mac. The first thing we can do is actually invoke this instance. So if we invoke, we're just going to do a simple curl. We're using the model of Qwen 2.5, 7 billion parameter instruct, and we're asking what is agentic AI. So while this is doing that, I'm going to open up another dashboard. And the second dashboard that we have is actually going to be vLLM. And what this actually is going to show us is, and we'll turn on our refresh, we can see our latency, our token throughput, how many tokens are we fitting through the pipe, right? We can see the scheduler state, and I'll explain all this here throughout this talk. But what we care about is that first time, that time to first token, and how long it actually took to get this first token. Now we sent this response, and we got a response back from the model. But now in Grafana, we're able to track everything that's actually going on. And so if we look at the time to first token, this took about our P99, which is great. And we can see that this took about 70 milliseconds for our response. Here's how much cache we actually use, our utilization. Here's this prompt length of our request. And then here's the actual response as well from the generation. So here's the request, which was about 50 tokens. And the response was between 200 and 500 tokens. And we can see that here. And it tells us exactly what it is. If we actually go in here, we can see that it was actually 269 total tokens with the completion tokens of 234. But we can actually measure this and graph this, not just for this single user, but for all of our users. And we'll go back into our talk. So we can see that this is healthy. We have the cluster up and it's running and all is good. So we'll go back. And now let's actually look at what's happening when we perform inference on this. So the first thing that happens when you send a prompt to vLLM and to a model to be processed and tokens to be generated, you need tokenization. This is the first thing that happens. It takes the prompt, the words, the characters, the language, and changes into numbers or tokens. And then from there, it takes those numbers and their matrices into like a table. Think of it as a table that has key value pairs. So call this when you hear KV cache, this is what that is. So it takes that and does what you call a prefill. This prefill is what the model uses to say, let me understand what this actually prompt is about and how do each word and everything relate together. And it stores that in the table for the matrices or the key value pair. And then from that, it's able to make its first prediction through the GPU. So it says, okay, based on what I know about this prompt, here is the first token I should generate. Now, after it generates that first token, it goes back, it looks at this prefill, along with the token is just generated, and it generates and predicts the next token. And it does that all the way to the end token. And then you have detokenization, where it converts it from the numbers back into the language. And that's how we get our response. And so what we care about is that time to first token, right? Which is going to be the prefill. This prefill says how long it actually takes to get the first token from the GPU. And then right here is going to be the total generation time. How long did it actually take? So that's actually what we care about. So after the first token, how long did it take to get to the last token, right? And so you can see all this, you can measure this, and this is what we are measuring in Grafana. And so these phases, when you're troubleshooting, are actually broken up into two distinct phases. First, you have the prefill, then you have the decode. So the action on the prefill is to process the prompt in parallel, right? It needs to process everything in parallel. That's the thing about GPU, because it gives you that ability to do that parallelization when it comes to the complex processing. It also needs to, for the hardware bottleneck, that's where it's going to measure in the GPU compute or the flops. So that's how it's going to measure when it comes to that hardware bottleneck. And then the user impact, when the user says it's taking a long time to get the first token, that's going to be your prefill. How long is it taking to formulate that key KB cache? And now the decode, this is where you generate one token at a time sequentially, right? And then you have your memory bandwidth, right? How much can you actually fit down the pipe? And you'll see what this means. So we'll talk about batching here in a moment, but how much information can you fit down on the pipe to be processed? And then that's going to be along with your throughput. And so this decode phase is going to be how long is it actually taking to get from the start token to the end token? And that will help us troubleshoot. Okay, I got my first token at this milliseconds, but every token after that is taking this long, and the whole thing took this long, right? And so if we break it down for our GPU that we have now, we have 400 gigabits per second memory bandwidth for the GPU. The weights of the Qwen 2.5 is going to be 14 gigabits on that 20 gigabit VRAM. And then from there, we are able to process, due to the bandwidth and the size of the model weights, 34 tokens per second on this GPU. Now, this is not just for a single user. We can actually batch and every user get the same experience. And we'll talk about that here in a moment, because this is what makes it powerful when you're doing this at scale with something like vLLM, because you can do some really good tricks to help manage this. And so if we look at this, you have your model weights with 14 gigabits that sits on that GPU. That's static. That does not move. Every time you prompt the model, that those weights go onto the GPU, and then they stay there until it's done, right? And so this is static. This is always going to take up that 14 gigabits. But then you have this KB cache. This is where you actually have that context window. Your context window is due to this, right? This right here, this 4 gigabits, this is going to allow us to process 38,816 tokens. That's the size of the context window. And what I mean by that is that's going to be the user message, system message, the generator responses, and all of the meshes, not just for one user, but every user. So if every user is using 4,000 tokens, and let's say you have 8 users can only use about 4,200 tokens, right? Or 100 tokens, 4,100 tokens. And if they go over that, that's when you're going to have issues with user experience. And so this headroom, meaning if you need to spike, you can increase the KB cache with something like vLLM to say, okay, I need that extra 2 gigabytes, right? Now, we're going to look at a couple different scenarios, but the first crash report that we're going to break down is going to be compute saturation under continuous batching. and actually what that actually looks like. Let me see, make sure I got enough time. And what this actually looks like. So how we're actually going is you have a single request, 34 tokens per second, right? You got all this GPU, but the user, because of the bandwidth, is only able to get 34 tokens per second. But the thing with batching, you can actually have multiple users, let's say 8 users or 20 users that can all fit on that GPU with, let's say 4,000 or 1,000 or 200 token context, however smaller context, like if you limit the context window, you can have 20 users getting 34 tokens per second on that GPU. And that's what continuous batching allows us to do. The second challenge that you'll run into is KV cache exhaustion. And I kind of mentioned this before, but what will happen is you have your KV cache, which only has 38,816 tokens available. But if users demand beyond that, you can't support that. So what's going to happen? The system is going to degrade. Users are just going to wait, right? If you don't have anything built into the system that says, with the rate limiting or to let them know that's what actually failed, they're just going to wait until all the batches have finished, and then they'll start getting responses, right? So you actually need to handle that, not at vLLM, but maybe at the API gateway or something to let the user know, like a back off or some type of system to have it built in. All right, so we're going to look at another demo with live crash and concurrent users. So we'll go back to the slide. And let's see where we're at. And we're going to our demo. And we're going to run one more demo. And so for this demo, we're going to start with a total of 32 concurrent users. So 32 concurrent users are going to send 200 tokens in their prompts. And so we go into demo and we load this. And I actually need to configure my environment and make sure we're good on time. I might set my key point. Give me 1 second. Let me make sure this is in my environment, and then we'll be good. So we'll go and we'll load this. And so what I'm doing now is I'm setting up my environmental variable so we can actually run this script. Like I mentioned, I got a new system, so I'm setting this up, and then we'll have our endpoint. So our endpoint will be configured, and we'll remove that, and we should be good. All right, let's make sure this is one more thing, and then we'll be good. All right, P and colon plus that. All right, now we should be rocking and rolling. It should be in there. Come on. I got you. Here we go. All right, so now we're sending 200 and then 232 concurrent requests. We're waiting on this. So the first one failed because I didn't have the endpoint configured correctly. I went in and I configured the endpoint, and now all requests are being sent, and we can actually see this start the spike, right? So we see the throughput increasing. We see the cache increasing to 5%, and all is being increasing. Now, if I increase this to, let's say, 100, this is really going to spike. Now, I have a lot more to cover, but we're getting to the end, so I'm going to kind of finish as quick as possible. But at the end, if you have questions, I'll stick around and answer your questions and also provide you a link so you can actually run this yourself. But now that we're doing this, we can see the throughput. You see the scheduler state? This is where we have that batching, right? So this is actually what manages the batching. And so here's the cache even increases even more when we went up to 100 users or 100 concurrent users, right? And then it dropped once it finished. And so this 20 gig GPU, right, 20 gig VRAM GPU is able to support over 100 concurrent users sending 200 tokens and generating a response. Now, that may not be a lot, but if you have a simple application and you're able to control that, you can get a lot done and you can manage a lot of users. Looks like we're coming to the end. If you all have questions, I am going to stick around. I'm going to wrap this up and then we can discuss more offline.
Thank you so much.
That was
doing
fun.
a live demo during a live broadcast is no easy feat.
Super fun. You had a lot of comments and applause. You also had comments from the folks backstage. I think you were blowing everyone's mind. That was awesome. Thank you.
No problem. Thank you all for having me. I really do appreciate it.
Do you want to do any last minute plug on this? I see there's the GitHub repo with it and the cloud credits.
So if you go to the GitHub repo, it'll give you everything you need so you can spin this up. The code is ready. The code is live. If you have questions about it, open the issue or reach out to me directly. But this would allow you to build the same demo that I have, along with some extra samples and everything that you need to spin up Grafana so you can test this out on your own on Akamai Cloud. And you also get 300 credits. So you're not going to really spend anything for this GPU. Just make sure once you're done, you in the lab and close everything down so you're not charged additionally when you're not using it.
And that's Peter and Jay. Yes, absolutely. We record the talks. Give us a couple of days, but on kubecrash.io, if you click on the tab that says past events, you see all the other 8 Kube crashes. This will be the 9th, and we'll put it up there. But Joanne, you also said you were going to host this on your website, right? And when you go back and you're answering the chat, maybe you want to put your website up or wherever we talked about earlier that you said you were going to give folks access.
Yes, it's already there. So you just go to DwayneLightfoot.com. It's already, the link is already live and available. If you just go to events, under the hood GPU, it has all the information there with the stack and all of the links that we discussed today. Everything's already there. So check it out. And all of my contact information is there. Thank you.
Super fun. Oh, you're getting a shout out from Eddie. That's the real deal right there. Hi, Eddie. Thanks for joining us again. Okay. Hi, Duan. Thank you so much. You can post those links in the chat afterwards. We're going to take you backstage. Danielle just did take you backstage, and we're going to bring on our next speakers.